So our next presenter is Emily Link, Ecologist with LIDAR Monitoring Project, U.S. Fish and Wildlife Service. And this is my bad because Emily was gracious enough to come in at the last minute and help us out. Don't tell the presenter that did cancel, but I'm way more excited about this presentation. Oh, wait, I'm telling them I'm online. My bad. So I'm super excited about this presentation, and I'm really thankful that you were able to come on such short notice. You were scheduled as our first presentation for next year. So thanks for coming this year. But because of that, I do not have your biography. So if you can share with folks for a minute, a little bit something about yourself. Thank you. You're going to want to change this because you're a foot taller than me.
Okay, so hi, I'm Emily Link, and I am the fire ecologist for the Southeast region with Fish and Wildlife Service. And I have worked on the LIDAR project for a little over 3 years now with John Wallace, and that's really relevant. So today I will be discussing the use of terrestrial LIDAR to monitor forest ecosystems around the Southeast, specifically more so on refuges because I am Fish and Wildlife. To begin, I'm sure many of you recognize the importance of monitoring, and I'm sure you always monitor what you're doing, right? You got to keep track, but I'm just going to highlight some of those aspects that are why it's actually really necessary to monitor your habitats. Within the Fish and Wildlife Service, our mission is to conserve, protect, enhance fish, wildlife, plants, and their habitats for the continuing benefit of the American people. But how are we able to evaluate and document our success in protecting and enhancing those habitats without measuring and recording various aspects about that environment? How are our resource management decisions able to be made without understanding what those current conditions are and understanding of some of those desired conditions to be? So accountability is a significant component of all work, but especially whenever the resources are of high economic value, such as a quality timber, or high social value, like a endangered charismatic animal. Organizations receive funding to ensure we're protecting our land and our endangered species. So the American people and those sponsors and the legislators allocating that funding want evidence that the management is effective. Accountability is very relevant in the world of prescribed burning because, as we all know, not everyone understands those benefits of burning, and some see it as unnecessary and too high risk. Monitoring also provides a better understanding of what a habitat or environment may currently look like in the species there. This is especially important in burning. As you all know, sometimes those fuels impact that behavior of that fire. And lastly, within management plans, objectives are established which decisions are based out of. And so monitoring provides reports on progress of those objectives and any environmental response. There are many aspects of the current monitoring programs that were identified as needing improvement. So one monitoring program is that data is collected and then it just sits in file cabinets or it sits on shelves or is lost in computer folders. This data may never be analyzed, or if it is, those results aren't in an accessible format for those necessary individuals and interested parties. While monitoring a particular habitat, especially one regarded as high value, there may be multiple people traveling to similar sites and gathering different plot information. So a biologist goes out, a forester goes out, a fuels tech goes out to the same area. This takes time and resources away from those specialists who should be instead writing plans and taking management action. Also, some refuges and forests may be lacking in staff and time and resources to have these productive monitoring programs. Many individuals are already feeling overworked and overloaded with responsibility as it is. So having this expectation of implementing a monitoring program would be very overwhelming. There might also be a lack of long-term commitment within programs when it comes to a monitoring strategy. While there may be support at the start of a program, if there isn't strong infrastructure in place, that could that won't sustain the efforts. And so that monitoring is lost, or an individual has monitoring in place and then they leave. And then the person who replaces them doesn't understand the monitoring, or they just don't see it through. There also needs to be a need for consistent structure measurement and empirical evidence to justify why we are doing these various restoration treatments in the ecosystem. This evidence is particularly important for treatments that seem destructive to less informed individuals. Public visitors may be upset seeing timber sales or mastication or prescribed burning. But by monitoring before and after those treatments, we're able to show the restoration of that habitat and show how the quality of that habitat is improved post-treatment. There needs to be better communication with the public and legislators who are allocating funds about why those treatments are necessary and the benefits of prescribed fire. A fire management officer who has been at a refuge for over 20 years and he knows the history of those burn units and he has a pretty good idea of what's going to happen when he puts fire on the ground, he doesn't need the monitoring evidence. He knows what's going to happen. But you know who does? The homeowners association of the new development down the street who are now seeing smoke in the air close to their new home. They might want some proof about why this fire is actually necessary for that habitat. So the solution to mitigate these monitoring challenges is terrestrial LIDAR. For those of you who are not familiar with LIDAR, it stands for light detection and ranging. And the technology uses light pulses or lasers to provide precise three-dimensional information. Traditionally, especially in the natural resource world, you may be familiar with the aerial LIDAR, which it maps the characteristics of the Earth's surface. But what we do is we use terrestrial LIDAR. So instead of looking down at the forest, we place a laser in the understory and it rotates in 360 degrees, sending out millions of light points. And those are sent back as points and distances and data points to produce a point cloud. And this 3D point cloud is a model of that plot. And then that model can then be analyzed for metrics. Metrics and measurements are extracted from that point cloud. So again, because of some of the current challenges or issues with effective monitoring programs, the interagency terrestrial LIDAR project began about 3 years ago, a little over 3 years ago now. There was this need for a repeatable, rapid, and affordable method of monitoring the ecosystem. Especially in fire, there's this need to measure the environmental response to fuel treatments and capture that vegetative change. The program is a way to assess those long-term impacts of treatments and assess the ecosystem quality over time. Another objective is to provide those land managers with empirical evidence to make more informed decisions to better manage these habitats. And lastly, a significant deliverable is the standardization of monitoring and language across agencies. Everyone's working towards the same goal. We all want to improve the environment and better manage our land, but we need a standardization of terms and in uniformity in methods so that we can more accurately and more efficiently measure results to get better results. So why is this method effective as a monitoring technique? Firstly, it is relatively cost effective. While the laser itself may seem expensive at about $25,000, it is an investment. And this investment, it gathers such a wide range of information about the habitat, and it could potentially replace costs of less effective and less efficient monitoring. There's very little training required. So while some traditional methods require classes to complete at a proficient level, our training from beginning to end of the monitoring protocol takes about 2 to 3 days. And that is regardless of a person's background knowledge and education. Traditional monitoring also has a large amount of human error and human bias in it. Perhaps the measurements are being done by interns who may not care about the quality of the data or fully invested in the process. Could be the end of a long, hot day, and that data accuracy may not be as the integrity of the data collection may not be there. Even if someone who does care about the data collection, they go through a plot twice and they may get different results each time. The laser collects data the exact same time every single time you press that button. And when the laser gets tired, you just change the battery. With each scan, data related to multiple metrics are collected at once. So rather than having to spend time collecting data related to separate aspects of a forest, at the press of a button, measurements related to that entire plot are captured within 3 to 5 minutes. Lastly, a major benefit of this technology is you're able to virtually revisit that plot 10 years down the road. So the placement of a leaf during those 3 to 5 minutes, you're able to visualize that in 10 years later. And you may look back at data that was taken 15 years ago and wonder, what was that technician doing? Why were they collecting that? And wish that they had done it a different way. But with TLS, that's no longer an issue. So what is our protocol? In the field, there are 2 types of plot methodologies involved for efficiently collecting TLS data. The tier 1 protocol is essentially, it's just a scan, and these take less than 10 minutes to set up and can be done by one person. I go out and I do tier 1 plots alone. The tier 2s are more physically intensive. These were created with traditional monitoring protocols in mind. So these have like field monitoring components, such as a Brown's transect, which measures the coarse woody debris, as well as a forestry aspect of the 10-factor prism. So these involve, you take a scan at plot center, and then you set up 10-meter transects in each cardinal direction from the center of the plot. And then moving along those transects, it's a presence absence vegetation sampling, as well as the field heights recorded and the litter depth recorded, and then coarse woody debris tallied. And we count the tree species within the plot and how many. Our spatial design is the plots are randomly generated across management units. In the past, we even generate more than we expect our crews to get, just so like some plots may not be physically accessible. If a refuge has historic monitoring plots that have legacy data, these are also incorporated into our plot locations, and those are actually prioritized by our crews for making sure that we rescan those plots with legacy data. The minimum requirement that we currently have is 1 plot per management unit, as long as that unit is less than 500 acres. Of course, this is dependent on that unit and dependent on what that land manager wants. So some units may have very different habitats within it, and so you want to increase the frequency of those scans within that area to help accurately capture that habitat. This coming spring, we are hoping to work with the statistician to ensure that our frequency and distribution across an area is capturing that landscape. In the field, our teams use field maps and Survey 123 to record the data. Once at the end of the day, the technicians offload the scan from the laser and convert the file type using our very specific nomenclature for naming those files. And then they upload these scans to USGS Eros. So these scans are very large, but Eros has the capabilities to store thousands of scans and process the data files, as well as display those resulting metrics. Here's a diagram of that workflow. And so Eros processes the files using the coding scripts that our research team has developed and refined, and it stores that original point cloud and any related data. They have also developed a database for researchers to download the data from, and they will also be launching an informative website for us next year. I will say at this point that there is a training required to upload the data and use our processing. This is largely to ensure that those files are named correctly, as if they're not, that messes up the processing, and also just for good data management. This is our list of our metrics that we are able to extract through processing. During processing, the ground points are all normalized to remove any influence of topography. And these plots are also cropped to a 15-meter radius, because the data beyond that radius does become distorted and it loses its integrity. Again, the great thing about this technology is as our analysis progresses and advances, we're able to rerun and reprocess these scans from past years. So for instance, in 2 years, if we're able to identify species, it automatically reruns all the past scans. And all that data is available for download then by anyone with the access. This is just a screenshot of that Eros data viewer, and this viewer has the raw data for the researcher. So you go in and you select what plots you're interested in. And then input your email, and within 24 hours, those folders are emailed to you along with a file explaining what each of those metrics mean. And even though Eros has developed this really great viewer, that's the raw data. And so Fish and Wildlife has developed an AGL viewer for managers, which kind of summarizes those metrics and its average per management unit, as well as you can select the specific plot and see those relevant metrics, and you're able to select between years, between scans to easily see that change. To evaluate the accuracy of the point cloud analysis, linear models are used to determine the relationship between that physical data and those point cloud predictions. So it's a physical data collected at the tier 2 plots, and then it's modeled against the point cloud analysis. But to create these models, enough data must be collected. And currently our processing is very good for like upland pine habitat. But as new refuges and locations come on board, they'll have varying habitats. So you perform 20 tier 2s, and then that data is sent to our data analysis and our data modeler. And if your habitat aligns with what our models have, then you're able to just do tier 1s. But if you need more data to build models for that specific habitat, then you have to do at minimum 100 more tier 2s. And once those initial baseline plots are implemented, only tier 1s are required past that point. A significant use of this monitoring, as with all monitoring, is to measure and quantify that change over time, primarily from a treatment. So these are point clouds at St. Mark's National Wildlife Refuge in northern Florida. And these images are a point cloud. This isn't a photo. This is a point cloud of a plot pre and post a prescribed burn. Now, you also get this visual from a photo plot, right? But this also has those metrics accompanied with it. So that empirical evidence. And it's at the push of a button. Within 3 to 5 minutes, you get all of that. And it's clear to any viewer that there is a reduction in understory vegetation and thus that reduction in wildfire risk. So it doesn't take a scientist to see the difference. These images can be shown to the public or for legislators to show the benefits of prescribed fire and help justify why we burn. If a prescribed fire is not meeting those fuel reduction objectives, these can also be used to justify why we may need some herbicide or increase the frequency or change the seasonality of the burn to get those desired results. If an area of the refuge is less burned, but you want it to look like a plot such as this, which is very well maintained, then you can compare those images and compare those metrics between them very easily to show why that less burned area needs a more aggressive treatment. So again, this is just another visual of that same plot. And then this is during the processing. So those are the heights and the density change after that fire. We currently have over 1,000 plots scanned, and that's constantly continuing and growing. This past summer, we also started rescanning at Piedmont National Wildlife Refuge in Georgia and St. Mark's National Wildlife Refuge in northern Florida. And next summer, we will be rescanning any plots from previous years that have undergone treatment. So our project focus is currently capturing that vegetation structure before and after treatment to show that fuel and risk reduction because we're fire. But there are so many different applications to be explored. And again, all that data is captured at once and easily accessible to any interested parties. So this technology is really great for getting that accurate tree measurement. Rather than using a prism to estimate the basal area, this processing identifies trees within plots, and then the entire tree bowl is able to be accurately accurately measured every 5 centimeters up and around the tree. And these measurements can be used to calculate like tree timber volume. And we have a limitation. Currently, we can't really identify snags. We're working through that. And at St. Mark's, which is my duty station, there are many species of interest. And one of these is the frosted flatwood salamander. And this TLS monitoring will be used to capture and measure their critical habitat. So that recovery program can better understand that ideal habitat for those delicate animals. There are also restoration projects in place to create more ideal conditions for the salamander. And TLS can capture those efforts and those results from those efforts. Another species of high concern at St. Mark's is the black rail. which is a small marsh bird. And researchers at Tall Timbers are using TLS at St. Mark's to gain a better understanding of what encompasses that bird's habitat. And this isn't replacing the current methods that those biologists are using. It is just adding another tool for their understanding of that bird's habitat. This is not replacing any jobs. It's just providing more data. It's providing more information. It's another tool. We also have red-cockaded woodpecker at St. Mark's, and we're using the TLS data metrics and overlaying those measurements with known locations of their clusters to really quantify what they are looking for in that forest structure, and then also identifying other areas of the refuge that they may be interested in or may be translocated to. And this past summer at Piedmont National Wildlife Refuge, there was a grad student who was evaluating the bird species richness using our TLS data of that forest structure and identifying any trends between those. So there are just so many applications for this data, and there's just so much potential for measuring species habitat and capturing the change of vegetation, either drastic from a natural disturbance such as a hurricane or a tornado, or more gradual vegetation response such as climate change. And again, all this data is collected at once. Now, if you have any questions, I know I went a little quick. But thank you just to anyone who has made this project possible and has contributed to the collection and analysis of this data, especially Scott Pockwinski, who's currently with the New Mexico Consortium. He has just dedicated so much of, and this project would not be as successful without him.
Thank you, Emily. Any questions for Emily here in the audience? Raise your hand if you do. Yes, sir.
Curious about for timber volume, can you find a 7-inch top?
Repeat that.
Yes, he asked if for timber volume, if you can find a 7-inch top, and yes, it measures the entire volume up the, like the entire diameter up the tree.
You could fully cruise timber.
Yes.
Yes, yes,
Yes.
yes.
You know, not if you find a 7-inch top, if you're in a different place in the country that has different top wood standards, different vertical top, you can define what that vertical top is. And so if you got a 4-inch cut off the top, it'll count the height of the 4-inch top. You divide.
Yes. So
Takes all the form classes that were developed back in the early 1900s out of the picture because it measures, like Emily said, every 5 centimeters. Think of it like Minecraft. You know, Minecraft, you've got these squares. That's all we see. That these squares are 5 centimeters. And so I can count the volume number of 5 centimeter squares in a tree. And so I can get the exact volume, basal area, canopy height. You know, we've poured around and calculating top-wood, old chip might be available above that 4 or 7-inch cut off the top. There's a lot of forestry stuff you can get out of it that you know, just seeing you cruise the timber with me.
Can you relay that to folks online?
So yes. And it eliminates the need of all the different tree structures as well, because it measures the entire volume of the tree. And if you move across the country and they have different standards, so rather than a 7-inch top, you can query the trees and the information for whatever your requirements are.
Excellent. Any other questions? We have none online. Yes.
Yes, the initial cost is $25,000, but it can be shared across like forest, and it can be switched in between and shared. And it just does offer so many different benefits.
We have one online question. Yes, Dan, go.
Do you think that drone? Do you think that drone LiDAR could become a tool due to its high point density at low altitude?
Currently, we do not support the LiDAR. It's not that we don't support it. We do not like the current state of the drone LiDAR. We prefer the terrestrial as it currently is.
Any other questions here in the audience?
I got a comment on what she said in terms of setup cost 25,000 at 2 minutes per plot. You got. It's real appealing.
And initially you do have to put in those more intensive plots to get that data baseline. But a couple years down the road, once we have those modeling, then it does take less than 10 minutes per plot. So that first year and that first establishment of those plots, you do have to do the more intensive data collection. Unless you already have historical data from that plot, we are working to just use that historical vegetation data.
How long is this?
About 45 minutes. So still quicker than some methods. Still quicker than some methods, and you are just able to gather you're able to gather such a wide encompass of information.
In pine, flatwoods, longleaf systems, feel pretty good about those models already. So the probability that you're gonna have to take those tier 2 plots and pine, flatwoods and longleaf systems is dramatically low. I think you're gonna be in pretty good shape if you're in longleaf.
So yes, and pine, flatwoods, and you will not have to. Our models are very good for that, so you don't really have to get those as intensive.
All right, time for one more, if there is one more. Yes, Jim.
What are the common technical issues with TLS and LiDAR equipment, and which are the vendors that are available?
So right now, we haven't had too many issues with the technical aspect of the TLS. Our biggest issue was our first year. It was actually just like the software and the offloading process. We were using an iPad in the field. And once we stopped that process, we haven't really had any issues now. We use the Leica BLK 360. We are working to develop our processing so that it is unit, you don't have to get that exact unit. We're just trying to do it with point clouds in general. But right now our methodology is the BLK 360 by Leica.
All right, thanks. So thanks, everybody. Round of applause.